Hello and welcome to another video. So in this video, I'm going to look at a different technique on solving integrals. And this involves using the Pythagorean identities to solve for the integrals that we will see, like with this example that I've written down here. So what if I want to integrate dx divided by x squared over x squared times the square root of x squared plus 9. Well, we wouldn't use ordinary u sub because that would be a little bit more complicated to perform a u sub. So what we're going to have to do is we need to use trigonometry. In particular, we want to use three basic Pythagorean identities that we have seen in previous math courses, right? The first one is we all know and love, right? Sine squared of theta plus cosine squared of theta is 1, right? That's the first one. The second one is if we just divide the first Pythagorean identity by cosine squared theta, right? That will give us tangent squared of theta plus 1 is equal to secant squared theta. And the last one is dividing the first Pythagorean identity by cosine squared theta. We'll get the last one, right? So we're going to use these Pythagorean identities to solve and get a much simpler integral that involves trig functions, okay? So what we notice here in this example here is that we want to look at this quantity inside our square root, x squared plus 9. Well, it looks oddly similar to the second trig identity, right? It's similar to the second one. So what we're going to do is we're going to use this second trig identity to replace the integral in terms of x's to an integral in terms of theta, right? So if I can rewrite x squared plus 9 so that it has a plus 1 in this quantity, right? What we can do is if I factor 9 to each term, I'll get x squared over 9 plus 1, right? And I can rewrite this first quantity here as 9 times x over 3 squared plus 1, right? So if you see here, we have an x over 3 squared, which is similar to the tangent squared theta here, right? So both of these are the same, and there's also a plus 1, right? A plus 1 is here, and a plus 1 is here as well, right? So one substitution is let tangent of theta equal to x over 3, right? So in this case, let x equal to 3 times tangent of theta, okay? All right. So if I just squeeze by here, well, we have x equals 3 times tangent of theta. And if we differentiate this equation, right? If we differentiate, we'll have dx is equal to 3 times secant squared theta d theta, right? 3 times secant squared of theta d theta, right? So now here comes the transformation. So this integral in terms of x would equal to, in terms of thetas, the following. dx is 3 times secant squared of theta d theta. So this is 3 times secant squared of theta d theta divided by, well, x is equal to 3 times tangent of theta. So we'll have 3 times tangent theta squared, right? Times the square root of Well, this would be 3 times secant of theta squared plus 9. Right? Plus 9. All right. And we can simplify this integral a little bit more. So if I go over here, right there is perfect. So this equals to the integral of 3 times secant squared theta d theta over 9 times tangent squared theta times the square root of 9 times secant squared theta plus 9, right? Plus 9. So this equals to the integral of 3 times secant squared theta divided by d theta, 9 tangent squared theta. And this would be 9 times the square root of 9 times secant squared theta plus 1, right? But secant squared of theta plus 1 is tangent squared theta, right? Let's see. Oh, I'm sorry. Okay, I made a mistake. So this is tangent. And yeah, this should be tangent. Sorry about that. So that's my mistake. Yeah, so this would equal to so tangent squared of theta plus 1 is secant squared theta. So therefore, our integral will be 3 times secant squared theta over 9 times tangent squared theta times, so this would give us 3 times secant theta, right? D theta. And this will equal to 1/9 times the integral of, we'll have an extra secant theta in the numerator, and we'll have a tangent squared theta in the denominator, right? Okay. And secant is 1 over cosine, and that is equal to 1/9 times the integral of cosine theta d theta over sine squared theta. Okay. And this is just a basic u sub, right? If I let u equal sine theta, du is equal to cosine theta d theta, right? So in u's, this will equal to 1/9 times the integral of du over u squared, right? So this equals to, by the power rule, 1/9 times minus u to the minus 1 power plus c. Okay. So we need to get back to x's, right? So we know that u here was sine of theta. So this equals to 1/9 or minus 1/9 rather. So I'm going to write it out as 1 over sine theta, which is cosecant theta, plus c. Okay. And to get back into x's, what we now notice here is that, well, we had this relationship at the beginning. Tangent of x is equal to x over 3. Tangent of theta is equal to x over 3. Excuse me. So on a right triangle, right, tangent of theta is the opposite side over the adjacent side. So the opposite side is x over 3. And to solve for the hypotenuse, right, this is just the square root of x squared plus 9, right? X squared plus 3 squared. Okay, that's how you solve for the hypotenuse squared. And so this is our right triangle that we need to use. right? So if I go back over here, right? So this is equal to minus 1/9 cosecant theta plus c, right? U to the minus 1, this is an exponent, it's not inverse, so don't make that mistake. So cosecant of theta, so if I look at this right triangle, right, so this would equal to minus 1/9 times the hypotenuse, the square root of x squared plus 9, divided by the opposite side, which is x plus c. And that is the final answer to our integral. Okay? So this is just a fancy trig sub, right? And this is one type of trig sub that we will encounter. And throughout the video and the other videos I will post, I'm going to write out some examples, and I want you to think about how to proceed to solve these integrals that I will write out. So here's another example. Try and do this on your own. Okay, so we have the integral of dx divided by the square root of x squared minus 49. Be careful, x has to be bigger than 7. All right, so it's equal to 7, then we'll have problems. So pause the video, and I want you to try to look at how to proceed solving this integral. I'll give you a hint, it's not u sub. All right, best of luck. Welcome back. So hopefully you've been able to solve this integral, but really we're going to use the other type of trig identity, Pythagorean identity, I should say. And it has to do with this one, sine squared theta plus cosine, actually, not that one. I was thinking about the other one. Tangent square root of theta plus 1 equals secant squared theta. This identity that we're going to use. Okay? So if you notice, we want to look at the quantity inside our square root. So if I do a big lighter color, so we want to look at the quantity x squared minus 49, right? That in itself, we can factor out a 49 to each of these terms, and I'll get x squared over 49 minus 1, right? Okay. And then even further, we can look at this quantity, and we can rewrite that quantity as 49 times x over 7 squared minus 1. Okay? All right? So x over 7 minus 1. So let's actually save this quantity here inside the parentheses. Because on this side here, okay, if I solve for a tangent squared of theta, right, this equals to secant squared of theta minus 1, right? As you can see, we have a secant squared of theta. It actually matches with, if I just erase this piece, it matches with this x over 7 quantity here. And there's also a minus 1 here and a minus 1 here. So if we just match up the terms, right, what we will get is we can say secant of theta is equal to x over 7. That's over 7. Okay. So we can express this relationship by a right triangle, right? Trig functions involve functions with right triangles. So secant of theta, right, Secant of theta is the reciprocal of cosine. So it's 1 divided by cosine of theta. Cosine of theta is the opposite. I'm sorry, cosine of theta is the adjacent side divided by the hypotenuse, right? So the hypotenuse in this case is x, and the adjacent side is 7 with respect to theta. So this side right over here would be x squared minus 49, right? So that's the right triangle that we want to use, right? So right triangle. Okay. So going back to our example, what we want to do is we want to solve for x here. And we'll say that x is equal to 7 times secant of theta. Okay. That's is equal to 7 times secant theta. Right? So if I differentiate both sides, I'll have dx is equal to 7 times secant theta, tangent of theta, d theta. Okay? Okay. So in terms of theta, right, so we had dx divided by the square root of x squared minus 49, right? So in terms of thetas, this equals to the integral of our dx term in the numerator. This is 7 times secant theta, tangent theta, d theta, divided by the square root of the square root of 7 times secant theta squared, right, minus 49. Right? Minus 49. So this equals to 7 secant theta tangent theta divided by the square root of 49 secant squared theta minus 49, right? Okay, so if I factor out a 49 to each of the terms on the denominator, so this equals to 7 times secant. Let me move over here. Secant theta, tangent theta, divided by the square root of 49 times secant squared theta minus 1, right? Secant squared of theta minus 1 is tangent squared of theta, right? So eventually we can reduce this integral down to be the integral of 7 times secant theta tangent theta divided by 7 times tangent of theta. And this is d theta up here. Okay? All right. Tangents will cancel, and also with the 7s. And this integral becomes the integral of secant theta d theta. Okay? And this equals to the natural log of the absolute value of secant theta plus tangent of theta plus c. Plus c. But we need to get back into x's. We're not done yet. You thought we were done. It's not over yet. We need to look at the relationship of the right triangle. So we have a secant of theta and we have a tangent of theta. So you already know what secant of theta is, right? We formulated it in our substitution. So it's equal to the natural log of the absolute value of x over 7. That was secant of theta. Plus tangent of theta. So tangent of theta, we would have to go to our right triangle here, right? Oops, can I make a check mark? This is our right triangle. So tangent of theta, right, is equal to the opposite side, which is the square root of x squared minus 49 divided by the adjacent side over 7. So that's tangent of theta. So this is plus the square root of x squared minus 49 over 7 plus c, right? This right here would be our final answer, right there, okay? Natural log of x over 7 plus the square root of x squared minus 49 over 7 plus c. Okay. So how about another example? This one. Okay. Here's another example. So I'm going to be writing out examples left and right. So here's another one. Dx divided by 25 minus x squared to the 3/2 power. All right. So pause the video and try to look at how to integrate this function, right? I'll be back here in a second. Okay, so hopefully you solved this integral. So once again, we don't use u sub, right? There's not a lot of information in this integral that will determine if we need to use u sub, right? So there's actually one other so there's actually the other Pythagorean identity that we want to use. So the first two examples, they use this identity, right? Plus one is secant squared theta, right? So they use that identity. But this time, right? So this time, what we want to use is this identity. Sine squared theta plus cosine squared theta equals 1. The very famous identity that everyone in the street knows, right? Sine squared theta plus cosine squared theta is 1. So if I solve this for cosine squared theta, right? Cosine squared theta equals to 1 minus sine squared theta, right? This is going to be important later on because the most of the work is going to rewrite the quantity 25 minus x squared, right? To match up with these terms on the right-hand side of this equation, right? So notice, right? 25 minus x squared is equal to 25 times 1 minus x squared over 25 squared, right? And so this equals to 25 times 1 minus x over 5 squared, right? Okay. So once again, right, we have this relationship. There's 1 on each of on the right-hand sides of each of those terms, right? And also, if I just match up term by term, right? We have a minus sine squared theta and we have a minus x over 5 squared. I should write the squared in here, right? So from here, so let sine theta equal to x over 5, right? X over 5. Okay. So sine of theta, this will incorporate a right triangle with that relationship, right? With angle theta. And sine of theta is the opposite side over the hypotenuse. So it's x over 5. Okay. And this remaining leg is just 5 squared minus x squared, right? Or 25 minus x squared, right? Or the square root of 25 minus x squared. That's how you find one of the legs, okay? So this is our right triangle that we want to look at. Okay, this is the right triangle we want to look at. And so we want to let x is equal to 5 times sine theta, right? 5 times sine of theta, okay? This is the substitution we want. And so if I differentiate both sides, dx is equal to 5 times cosine of theta d theta, right? So this is the key info that we need, right? So the integral in terms of x, right? Let me rewrite this. Minus x squared to the 3/2 power is equal to, in terms of theta, this equals to, well, dx is 5 times cosine of theta, 5 times cosine theta, d theta, divided by 25 minus the x right here, which is 5 times sine theta squared to the 3/2 power. All right. So that's in terms of theta. Now, to reduce down this integral, so we'll have 5 times cosine theta d theta divided by. So this is 25 minus 25 sine squared theta to the 3/2 power. Okay, this is going to be slightly tricky, right? So we can rewrite this integral as the integral of 5 cosine theta d theta over. So I'm going to write out the denominator like this. Okay. So the square root of 25 times 1 minus sine squared theta cubed. Okay. All right. So you can rewrite it like this. But if you notice, right, the square root of 25 is 5, and the square root of 1 minus sine squared theta is just cosine of theta. So what we will have is so 1 over 5 cubed. So this will be 1/25 on the outside of the integral. And we'll have times the integral of, let's just write out the numerator and denominator in its entirety. So, and this is times cosine cubed of theta, right? Okay. And so this equals to 1/25 times the integral of 1 over cosine squared of theta, which is secant squared of theta d theta. Okay. Ooh, antiderivative of secant squared of theta. This equals to 1/25 times tangent of theta plus c. Okay, plus c. And what is tangent of theta? So getting back into the x terms now, we have to look at a right triangle, right? Tangent of theta is equal to the opposite side over the adjacent side. So tangent of theta in this right triangle, this equals to x divided by the square root of 25 minus, let me just write it over here so you can see it. Over here, so tangent of theta is equal to the opposite side divided by the adjacent side. So 25 minus x squared. So that is tangent of theta. And if I go down here, so this equals to 1/25 times x divided by the square root of 25 minus x squared plus c. Okay. And that here is the final answer. Final answer. So there's that other example. So if you see the summary of what to do here, so let me write out the summary of what to do for a trig sub. So one variation is if you have this relationship, x squared minus a squared, you want to use x is equal to a times secant theta, right? A times secant theta. Next, this is the right triangle, by the way. If you have a relationship like this, so for any constant a, right? So the other one is if you had the hypotenuse here, you want to use that x is equal to a times sine theta. That's the other one. Okay. And also for the third type, third relationship, okay? So the third type, let me go back to my examples. Yes, so the third type is this one. X is equal to a times tangent of theta, right? So in summary, for any constant a, you'll have these relationships here, right? You want to use these substitutions for each of the corresponding relationships between x and your real number a. So, yeah, so keep in mind about these different types of relationships here. But that's essentially it, right? So the last one, the last example I want to write out is this one. This might take a little bit more work, but I know you can do this. So try to work out this example. Dx divided by the square root of 3 minus 2x minus x squared. Okay. So pause the video and try to look at how to proceed with solving this integral. Okay, so I gave you some time to look over this example. So the tricky part here is we want to involve the complete the square method, right? Complete the square method here. All right. And it involves looking at the quantity inside of our square root, right? So what I'm going to do is I'm going to rewrite this integral as dx divided by the square root of, I'm going to factor out a minus sign. So this looks like this minus of x squared plus 2x minus 3. Okay. So I rewrote the integral to look like this, right? And what we want to do is complete the square on the quantity x squared plus 2x minus 3, right? Oh, that looks weird. Minus 3. Okay. All right. Because we needed to have two perfect squares of these types appearing. X squared minus a squared, or a squared minus x squared, or x squared plus a squared, right? We want to look at these types of variations in our integral here. right? We have an x squared and a 2x term, right? That won't work. So we need to have either of these types of relationships showing up in our integral, right? So, okay, so to complete the square, we want to look at the first two terms in our of our trinomial here. Okay, so we have x squared plus 2x plus, I'm going to do a blank here, then minus 3, and then we need to minus that same number again, right? To complete the square, we want to look at the coefficient on the x term, which is 2, right? Divide that number by 2. That gives us 1. All right. Finally, when we square that number, and that would be the number that goes into these yellow spaces here. So in this case, 1 squared would be 1. So we add 1 and we subtract 1 here too. Okay. By doing this, right? By doing this procedure, these first 3 terms become a perfect square. And these last 2 terms, we can combine them to be a minus 4, right? So altogether, so this would equal to x plus 1 squared minus 4, right? So that's another way to write out x squared plus 2x minus 3. Okay? So it's written out as x plus 1 squared minus 4. Okay? And then we're going to replace that integral, this integral right here, equal to, so this equals to the integral of dx divided by the square root of minus x plus 1 squared minus 4. Right? Okay? And so this equals to the integral of dx divided by the square root of 4 minus x plus 1 squared. Okay? All right. So if you notice, right, this quantity 4 minus x plus 1 squared is similar to the a squared minus x squared quantity, right? Right, it's similar to that, right? But the a number, our constant, is 4, and the x term in this case is x plus 1, right? And the substitution we used with this quantity, a squared minus x squared, was when x is equal to a times sine theta, right? So similarly, we're going to use the substitution that x plus 1 is equal to 4 times sine theta, right? Just replace the x with x plus 1 and then the a with 4, right? So this is the substitution we want. I hope this makes sense. Okay. So in this case, x would equal to 4 times sine theta plus minus 1. Minus 1, excuse me, right? Minus 1. So if I differentiate both sides, dx is equal to 4 times cosine theta d theta, right? Derivative of 1 is 0, so you'll have dx is equal to 4 times cosine of theta d theta. All right? So what do we have now? So we know that dx divided by the square root of 4 minus x plus 1 squared in x's equals to this integral in thetas. So this integral is equivalent to the following. So we have the integral of 4 times cosine theta d theta divided by the square root of 4 minus, so this would be 4 sine theta plus 1 minus 1 squared. Okay. So if we combine like terms, we see that 1 minus 1 is 0, so these will cancel. And we have now that this integral equals to the integral of 4 times cosine theta d theta divided by the square root of 4 minus 4 cosine, let's see. Oh, I made a mistake. A squared. The a squared is 4, so this should be 2. All right. I've made my mistake here. So there should be 2. And this is 2, 2. Oh boy. Okay, so this here is 2 and 2 here. And this should be a 2 over here. And then that works. Okay. Why did I mess that up? Okay. So we are on schedule. All right. So hopefully you caught that mistake. Yeah, so the a is 2, right? Since a squared is 4, a is 2, right? So, yeah, we'll have 4 minus 4 cosine squared theta on the bottom, right? And what we have now is sine squared theta. Okay, this should be 4 sine squared theta. Okay, so this equals to the integral of 4 times cosine theta divided by this should be a 2 here. That's a 2 here. And we caught that one too. See a lot of 2's here. So it's 2 cosine theta divided by 2 times cosine theta, d theta. Sweet. Okay, so that equals to d theta, which equals to theta plus c, right? But we need to get back to x's. What do we know? We know that x plus 1 is equal to 2 times sine theta, right? So that means sine theta is equal to x plus 1 over 2, right? So theta is equal to inverse sine of x plus 1 over 2. Okay, so this would equal to inverse sine of x plus 1 over 2 plus c. Plus c. And yeah, so minus 1. X plus 1 over 2 has to be in between -1 and +1, right? So the definition of inverse sine of x, right? But anyway, regardless, that is the examples on integrals using trig substitution. So I want you to try out these examples. So the textbook is calculus curly. And the addition is third, so bridge. There's 4 of them, but this will be the first but that's the textbook I'm using. But I want I want all my students to hand in these problems, right? Okay. So, section 8.4. And I want you to work on these problems to hand in. So 42, 50, and 64. Okay. Here's just various examples of trig integrals that we've worked with. But next time, I'll be getting into more integrals in the future. So thanks for watching. I'll see you in the next video. Take care.